steps to make it less bad, but
Well,
then other people are trying to undo those steps.
That's exactly. I was
Um,
about to say you got people that are in favor for it, and then people who are just going right against it the whole time.
yeah. Okay. No crow. Oh. Isabel go to the no. Xavier. Mike. Two. Here and then Serena, right? I'm clear for this. Well, if we end up with so few people, I might just have the lab off till next week because we'll do it this week or next week. But chapter 22 homework is due on the 12th. That's this Thursday. Sorry, my brain is set to my class for on Monday, Wednesday. The chapter 22 quiz is also on the 12th. So we'll be finishing chapter 22 today. We'll start chapter 23. Because of the timing of the test, the chapter 23 quiz will be on Blackboard online. I'll go over that when it's a little closer to happening. We should have a lab today if everybody gets here, but if we only end up with 4 people here at lab time, we're either having a lab this week and not next week, or the other way around, because we're ahead of schedule on the labs. Just how things worked out. So we're going to, the current plan is that either we're going to have next week available for him.
No problem.
Next week will be available for makeups, or yeah, that's the current plan. Next week will be available for makeups, assuming people get here. So let's get on finishing chapter 22. We're talking about sedimentary rocks. Sedimentary rocks can be classified according to the origin of their constituents, where the stuff that made them up came from. There's 2 main types. You can have clastic or detrital sediments. These are just pieces of rock from other rocks. Sand and mud made of tiny fragments of material and like gravel. Clastic sediments are just from the solid fragments or detritus that erode from pre-existing rocks. Chemical sediments are sediments that come from dissolved minerals in solution. So an example of chemical sediments, halite or salt generally is deposited as a chemical sediment. It dissolves in water, the water evaporates away, leaving behind a salt flat. And then limestone is a chemical sediment commonly, where calcium carbonate gets dissolved in water. So classic sedimentary rocks are classified according to the grain size of their components. So shale, for example, is composed of very fine grained particles that were initially mud. Sandstone is composed of sand-sized particles. And then if it's composed of little pebbles, if those pebbles are rounded and they've been carried in a stream, that's conglomerate. If they're angular, that's called breccia.
Yes, aren't the sand-sized particles like really tiny? Or are they?
They're the size of sand. I mean, we'll have the, I don't remember if I actually have the sand classification, but it's like,
I mean, when I think of the size of sand, I just think of like a grain. Tiny.
They're small, they're like less than a millimeter, but the particles of shale are like less than a 16th of a millimeter.
Okay, so they're all really.
Well, okay, so I think sand, the range for sand is something like 2 millimeters to a 16th. I don't remember the exact range. I have a table somewhere. but they're just size classifications. The line is basically arbitrary. But, and then the difference between conglomerate and breccia is that conglomerate has rounded pebbles and breccia has angular pebbles. Rounded pebbles generally need to be carried in a stream for a long time, so they appear in different places. So they have to be worn round. And clastic rock particles are generally held together by calcium carbonate or silicon dioxide. So here is a short video about the formation of plastic sedimentary rocks. And I'm not sure I have the sound settings correct. No. There we go.
Clastic rocks are the most common type of sedimentary rocks found on Earth's surface.
This mini video describes how these rocks are formed.
Check out this related video for a discussion of the classification for all types of sedimentary rocks.
There are 3 steps in the formation of clastic sedimentary rocks. Clastic sediments are composed of fragments of rock. In fact, a clast is a technical word geologists use to describe a rock fragment. These fragments weathered from pre-existing rocks to form sediment of various sizes. This sediment is then transported away from its source area, and finally it is deposited and converted to form a new rock through lithification. So let's take a closer look at these processes, starting with the breakdown of rocks by weathering.
Rocks break down on the Earth's surface to form sediment. The resulting rock and mineral fragments may then be further physically or chemically weathered to form even smaller grains or other minerals.
For example, individual feldspar minerals are weathered out of this igneous rock. Notice the grains of sediment at the base of the outcrop.
Sediment like this is then eroded by transportation agents such as streams, winds, and glaciers.
This river in Alaska is carrying a high sediment load as reflected by the muddy color of the water and the sand and gravel bars in the stream channel.
Much of western Oklahoma and northern Texas lost their topsoil to winds during the Dust Bowl era of the 1930s, and we see similar dust storms today in drought-stricken western states.
Elsewhere, dust and sediment from the Sahara Desert may be transported across the Atlantic Ocean to Central and North America.
Finally, sediment of all sizes is transported by glaciers. For example, the dark surface of the Reed Glacier in Alaska reflects that sediment is exposed as ice melts. If we look closely at the glacier, we can see layers of sediment encased in the ice.
The last stage in the formation of clastic sedimentary rocks occurs after the transporting agent loses energy and the sediment is deposited.
As more and more sediment builds up, the material at the base of the pile is compacted. Compaction squeezes out spaces between grains and pushes the grains closer together. Finally, chemicals precipitate out of water to cement the grains together and form a rock.
These processes result in sedimentary rocks like shale, sandstone, and conglomerate.
So as we finish up, how confident are you that you can meet the learning objective for this lesson?
By the way, yeah, so sand is 0.05 to 2 millimeters in size, is the way it's defined. And shale is even small. The particles in silt are even smaller than that. So sedimentary rock, classic sedimentary rocks can vary from very fine grain. The shale, you can barely see the particles. Sand, you can see in sandstone, you can see and feel the particles, they're sort of medium size. And then conglomerate, large, visible individual pebbles. So here's the scale. Gravel is bigger than 2 millimeters in size. If they're rounded pebbles, you get conglomerate. If they're small, if they're angular pebbles, it's breccia. Sand is from a 1/16 to 2 millimeters for sandstone, and mud, which forms shale, is less than a 1/16. Yeah. It's still somewhere else, it was 0.05, it could be a 20th, but it's about the same cutoff. So, but I mean, this line is arbitrary. So chemical sedimentary rocks are divided into two basic types. Either that mineral gets precipitated out of solution by living things, or no living things are involved. Those are organic and inorganic. In both cases, the chemical sediments are composed of minerals that were transported in solution to their eventual deposition site. Then either they're consumed by living things and turned into hard parts of those living things' bodies. That's something we as humans do. That's how we make our bones. But or they could just, the water can evaporate and leave behind the precipitate. The mineral can precipitate out. That's how things like dripstone, like stalactites and stalagmites in caves form. As the water drips, it evaporates, the calcium carbonate solidifies and forms a new layer of rock. So some examples of inorganic and organic sedimentary rocks. Inorganic limestone is calcite. You can have limestone that forms without any living things involved. Just the calcium carbonate is dissolved, it then evaporates. The water evaporates, you leave behind calcium carbonate. This is like dripstone in caves, things like that. Evaporites. Evaporites are various things that are called generally when you have like a lake bed or something, it evaporates. There's just things like halite, rock salt, gypsum, which is so calcium sulfate with water. Dolostone is dolomite, which also forms calcium magnesium carbonate. And then inorganic chert is chemically precipitated silica. The inorganic chert you've probably heard of is flint. But the more general term is chert. Flint is a specific variant of it and is technically not everywhere in the world. So the more general term is chert. But it's what it is you get some void and silica starts to concentrate and precipitate out in that void, and you get like a nodule of very tiny, tiny crystals of silica. And that is how you get flint or chert. Then organic, we have biogenic limestone. These are things like the calcium carbonate remains of marine organisms. Mostly single-celled tiny ones. So algae, Formiferia, but you can also have larger things like seashells and such in them. But primarily it's tiny single-celled stuff. Then there's biogenic chert, which are the silica remains of marine organisms. These come from things like radiolaria, diatoms, sponges. Again, mostly single-celled life forms that instead of using calcium carbonate extracted from water, they use silica. You can literally buy bags of the sediment this forms from, called diatomaceous earth. People use it for all kinds of stuff. Usually in aquariums, but it gets used in a bunch of things. It's readily available, and that's basically biogenic chert that hasn't been glued together yet. And then coal. Coal is considered a chemical sedimentary rock. even though coal is not a mineral. And it's the compressed remains of terrestrial plants. It's basically carbon. But yeah, it comes from plants. Oil comes from marine life, and coal comes from land life. Oil and gas come from marine life. So organic sediments are formed largely by the actions of organisms that remove the minerals out of solution. You have some animal that extracts the mineral to use it as a shell, usually an outside covering. For example, many large and microscopic organisms in the ocean extract calcium carbonate out of seawater to construct skeletal and shell material. And then as these organisms die, their hard parts come to rest on the bottom and eventually lithify into organic limestone. So here's an example of organic limestone made of microscopic organs. That's the White Cliffs of Dover, which are chalk deposits. Chalk is made of basically calcium carbonate. Though coal is not formed from minerals carried in solution, it is still classified as an organic sedimentary rock because we needed somewhere to put it. Basically, it's formed from the lithified remains of ancient plants. You take plant material, you compress it, and you bury it and compress it without oxygen for a very long time, and compress it, and eventually you get coal. Now, inorganic chemical sedimentary rocks are commonly formed by the evaporation of water. As the water evaporates, the dissolved minerals in the solution precipitate out. And examples of inorganic sedimentary rocks include things like halite, which is rock salt, gypsum, which is calcium sulfide, and various cave deposits, which are generally calcium carbonate. So here are some inorganic chemical, sedimentary rocks.
Chemical sedimentary rocks are one of the three major types of sedimentary rocks. This mini video explains how they're formed.
Imagine you took a tablespoon of salt and dissolved it in this small beaker of water. Then you added the water to a pan on the stove and cranked up the heat.
As time passed, in this case about 4 minutes speeded up, the water would gradually evaporate and the salt concentration in the remaining liquid would get progressively higher until the salt began to precipitate out of solution.
You can see the salt crystals forming here and along the edges of the pan. Eventually, when all the water is gone, the pan will be coated with the same salt that was originally dissolved in the water.
Essentially the same thing happens in nature, just not as quickly. This occurs when water in isolated seas or lakes evaporates, leaving behind dissolved minerals.
For example, ancient Lake Bonneville covered much of Utah 10,000 years ago. Most of the lake dried up, leaving the flat lake bed covered in a layer of salt.
Because these chemical sedimentary rocks form by evaporation, they're known as evaporites. As seawater evaporates, the concentration of salts changes and the different rocks are formed.
Gypsum will precipitate first, followed by rock salt as salt concentrations increase in the shrinking water body.
Minerals are also dissolved in lesser concentrations in groundwater and freshwater lakes and rivers, and are also concentrated in hot waters associated with thermal features such as hot springs and geysers.
Precipitation in these cases occurs when there are small changes in water chemistry.
For example, water evaporates in caves to leave behind limestone deposits. Each water drop loses carbon dioxide and deposits a film of the mineral calcite, which eventually builds up to form features such as these stalactites.
Gases are also lost as warm groundwater comes to the surface and minerals precipitate to form travertine, a type of chemical limestone which forms these terraces in association with hot springs in Yellowstone National Park.
Elsewhere, silica-rich groundwater may replace limestone to form irregular chert nodules, or produce chert when it precipitates in buried trees to form petrified wood.
So to summarize, chemical sedimentary rocks are typically formed as a result of evaporation or precipitation from mineral-rich waters.
Finally, how confident are you that you can successfully meet the learning objective for this lesson?
And there's a very impressive case of travertine in England at a place called Witch's Cave, where that there's spring water coming over an edge, and people have hung various things up in the water, and they get covered in rock and basically lithified. So there's like teddy bears and other random things that have been lithified at this place because it's got a very fast acting process. So some characteristics of sedimentary rock that are used by geologists to get a better understanding under the conditions where these rocks are deposited. So some things you can look at are things like rock color, the rounding of the grains, the sorting of the grains, which is, are the grains well sorted? Are they all the same size? Or are they various mixed sizes? Bedding, how they layer on top of each other. Fossil content is very important because it can be used to date rocks, because fossils only live during, the things that make fossils only lived for certain periods of times. Things like ripple marks, mud cracks, footprints, and even raindrop prints between the rock can help reveal the rock's origin and its history. So the color of rocks can vary quite a bit, and it can tell you interesting things about the sedimentary rock. So gray shades are pretty common in sedimentary rock. This indicates the rock was deposited in shallow, well-aerated marine water. Shades of yellow, brown, and red indicate the rock was deposited on land above sea level where there was abundant oxygen, because these yellow, brown, and red colors come from iron oxide. So basically what happened is that the iron compounds had a chance to rust. So there was plenty of oxygen for that to happen. Dark gray to black rocks contain lots of organic carbon, and this accumulated in stagnant oxygen pore areas. And the most extreme case of this would be coal, which is basically just organic carbon. And it happens, basically you bury organic material at the bottom of a swamp. And then you compress that for several million years. But yeah, peat is what turns into coal, basically. Now, grains can also, the rounding and size of grains can tell you about the history of the rock as well. Angular grains, so spiky grains, indicate the rock with sediments weren't transported very far. While rounded grains indicate great transport distances and vigorous wind action that wore away the sharp edges. Because normally when rock fragments form, they're irregularly sharp edged. They get rounded by wearing down as they're carried along in streams and such. Larger grains indicate strong currents deposited the sediments, while small grains indicate a very quiet environment existed when the sediments were deposited, because the faster that a stream moves, the larger the particles it can carry, which we'll get into in next chapter. Now, sorting is the degree to which sediments are separated according to size. Well-sorted sediments consist of grains that are all about the same size. Well-sorted sediments generally have been transported great distances over long periods of time by light streams. While poorly sorted sediments comprised of grains of vastly different sizes, they indicate short transportation distance and or time, or their transportation wasn't by water. Glaciers don't sort sediment. That's one of the things you can differentiate sediments dropped off by glaciers, is that the sediments deposited by glaciers don't get sorted. Then there's how the layers of sediment form. So bedding or stratification is the layering that develops as the sediment gets deposited. Bedding can either be very obvious or subtle. You can have very thin, hard to distinguish layers that are very similar to each other, or you can have very clearly different thick layers that are easy to differentiate. In general, bedding is horizontal because most sediments come to rest due to gravity. You know, they're settling in the bottom of a lake or something. In some instances where there's strong water or wind currents present, you can have tilted bedding. For example, there are places where there are basically solidified dunes preserved in some deserts. Also, you can have cases where you had horizontal bedding and then something happened to tilt it. This can be called cross bedding. So here's an example of bedding in sandstone. You can see the clear layers. And some are thick and some are thin. Now, the most distinctive and interesting feature in many sedimentary rocks is the fossils it can contain. And the fossil is the remnant, remains or an imprint of, or any type of trace of an ancient organism preserved in the rock record. It could be the hard parts preserved after the soft parts have rotted away. It could be, sometimes the soft parts preserved. It could be the shape of the animal preserved. And so one of the primary ways that we date sedimentary deposits is by the fossils of them. And yeah, so lots of things can be preserved as fossils, and fossils can also include things like tracks and footprints and things. So like there's some places with dinosaur footprints that are preserved. You can actually go see. So here is a video about
fossil formation. At the scene of a crime, detectives look for fingerprints. The criminals are gone, but they may have left behind clues. Similarly, in the world of biology, many organisms that are now extinct left behind clues that they existed. These clues are fossils, the remains or traces of organisms that lived long ago. There are many kinds of fossils. Some are imprints left by organisms in the mud that later changed to rock. Sometimes an entire organism is found. In March 1990, for example, a whole mammoth was discovered frozen in ice in Siberia. Amber is hardened tree sap that has been preserved in the earth for millions of years. Insect fossils have been found trapped and preserved in amber. Most fossils, however, are the remains of hard parts of organisms, such as bones, teeth, and shells. Most fossils are formed in sedimentary rock. Sedimentary rock is made up of layers of clay, soil, sand, and other earth materials. Sedimentary rock usually forms in water. When an animal that lives in the water dies, its body may sink to the bottom. The soft parts decay quickly, but the bones or shells may remain and become covered by sediment. The sediments build up layer by layer. Great pressure pushes the sedimentary layers together. Slowly, through chemical processes, the sediment and bones or shells change into rock, preserving the shape of fossil bones or shells in the rock. Two types of fossils found in rocks are molds and casts. Molds are formed when an organism is buried by sediment that changes into rock. The organism decays and leaves a mold or opening. Sometimes a mold fills with sand or mud. Then the sand or mud hardens and a cast is formed.
So those are fossils. That was sedimentary rock. Now let's talk about metamorphic rock. So metamorphic rock are rocks that have been changed by heat and pressure. As you know, we've already learned, igneous rocks formed by the crystallization of magma that generally forms deep within the earth, while sedimentary rocks are deposited at or near the surface of the earth. Metamorphic rocks form in between. They form in conditions below where sedimentary rocks form and above where igneous rocks form. So places where there's lots of heat and pressure, but it's not enough to melt the rocks, but it is enough to change them. And in general, metamorphic rocks form when the pressure and temperature conditions lie between the other two rock types, and when those conditions are different than the ones where the rock initially formed. So metamorphism is that process of conditions within the earth that result in the changing of the structure and mineral content of a solid rock without melting it. Now, any type of rock can be metamorphosed. You can have igneous rock be metamorphosed, sedimentary rock be metamorphosed, or even other metamorphic rock be metamorphosed. Sometimes you have like a chain of metamorphosis, more from less metamorphosed to more over time. So heat, pressure, and chemically active fluids are the primary agents of metamorphism. So heat and pressure will break some of the mineral bonds of the original mineral, and the fluids serve to allow the movement of ions around. So you can have minerals changing, you can have minerals recrystallizing, forming new crystals that are different, and you have a different structure. So when we talk about a metamorphic rock, there is a parent rock, which is the rock you had before the metamorphosis happened. So the original rock before metamorphism takes place. So in addition to heat, pressure, and fluid activity, the composition of the parent rock helps determine what metamorphic rock forms. So for example, if you take limestone and expose it to high temperature and pressure, but mostly high temperature, it will recrystallize to form marble. If you take sandstone and apply, again, high temperature and pressure, it will recrystallize to form quartzite. So the overall process of metamorphism can change both texture, the size of the crystals, and the mineral composition of the parent rock. Or metamorphism can only change one of these characteristics. So both of the examples I gave, the mineral composition doesn't change because they both start with one mineral and end with the same mineral. So limestone and marble are both made of calcite. Quartzite and sandstone are both primarily made of quartz. So here are some examples. And they're in two categories. They're foliated rocks and non-foliated rocks. Foliated rocks occur in situations with differential pressure, more pressure in one direction than the other, which causes the grains to flatten out and rearrange, and you get like banding and such. So shale will turn into slate, which has clay, quartz, mica, and chloride in it, with flying grains and slaty cleavage. Slate, basalt, shales, basalt or slate can turn into schist or schist. And you go from clay, quartz, mica, and chloride to chloride, plagioclase, mica, and garnet. As coarse grains, it's well foliated. And shale, granite, slate, and schist can turn into gneiss, which will have plagioclase, garnet, kyanite, and sillimanite. And it has coarse grains and light and dark colored bands. So that banded rock we had in rock identification was nice. If you start with limestone, and you for non-foliated rocks, limestone turns into marble. The key mineral in question is calcite. It stays calcite. The characteristics, you get these coarse interlocking calcite grains. That shiny other metamorphic rock from our lab was marble. Sandstone turns into quartzite. It's made of quartz. You apply to coarse interlocking quartz grains. And shale basalt or any sort of fine grained rock can turn into hard fells, which has lots of mica and quartz in it. You get fine grains and variable composition. So in general, if the parent rock contains only one mineral, the metamorphic rock will also be composed of the same mineral. Because generally the process of minerals changing involves swapping material with another nearby mineral. For example, limestone will metamorphose into marble, and they're both made of calcite. When limestone metamorphosed into marble, the structure of it changed, but not its chemical composition. So here is limestone, and here is marble. So as the limestone recrystallizes, the various fossils in it are destroyed. And the change from sandstone to quartzite is another example of the metamorphosis of a rock containing one or more mineral. Both sandstone and quartzite are composed of silicon dioxide or quartz. And when you apply sufficient heat and pressure to sandstone, the grains fuse together to form a very resistant rock, quartzite. So quartzite is much tougher and harder than sandstone, because instead of the grains being sort of loosely glued together, they've grown together from the heat and pressure and recrystallized into each other. And so it's much harder and more resistant to.
Are quartzite and quartz a part of the same?
Quartzite is made of quartz, so it is called quartzite.
Yes.
So silicon dioxide is quartz. Sandstone is also mostly made of quartz. The particles are quartz, they're just small. Quartz is a very common mineral. It's like the second most common type of silicate.
What is it like in the world? What is it mostly used for? Like
What, quartz?
Yeah.
All kinds of stuff. I mean, we use it to make glass. We use it to make we use it to extract. If you have very pure silica sand, you use it to extract your sand. Anything that uses sand is generally using quartz. Yeah, lots of things. Many things.
good that common.
Yeah, no, it's one of the most common minerals in the world. So, so when sufficient heat, because the most common type of mineral is silicates. Quartz is just pure silica. So it's, yeah. And so there's commonly quartz in lots of stuff. Now the crystals aren't very big, so they turn into like sand particles because they're tougher than the surrounding minerals. So they fall out as sand grains. But when sufficient heat and pressure can apply to sandstone, they fuse together to form quartzite. Now, if the parent rock is composed of several minerals, the process of metamorphism can create a new suite of different minerals. So these can be formed in response to the escalated heat and pressure conditions. We basically have ions from one mineral moving to another, things like that. Minerals sharing chemical components with each other. So for example, shale is a very fine-grained mixture of several minerals, quartz, clay, mica, and chlorite. And depending on the degree of metamorphism, shale can be progressively changed into slate, schist, or gneiss. And this depends on the temperature primarily. And so you get different minerals at different temperatures, basically. Also, metamorphism is a common way you can have metamorphism leading to the growth of larger crystals of things like aluminum oxide, which is corundum. That's how you get things like rubies and sapphires. I believe they primarily form in metamorphic rock. So here's sort of this process of shale turning to slate, turning to rhyolite, to schist, and then lastly to gneiss. And this is, as increased temperature and pressure. And if you went beyond the temperature and pressure that gneiss forms at, the rock would melt. So there's basically three types of metamorphism that can occur: contact, shear, and regional. Contact metamorphism is when magma comes in direct contact with the parent rock. So what's happening here is primarily we're just cooking it. Changes in the parent rock are primarily due to very high temperatures, but not much massively increased pressure. So this is a common way that marble forms. Immediately next to the magma, intense metamorphism results in the formation of very coarse-grained crystals. And as you move away from the magma, the crystals will be finer grained. And a contact metamorphic zone occurs when a parent rock is intruded by molten magma. Magma rises up through the parent rock. Shear metamorphism results from the intense pressures that exist in active fault zones when rock units slide past each other. So this is primarily pressure. You get mechanical deformation, like bending and recrystallization of minerals, result from the heat, pressure, and movement of fluids as rock units slide and shear past each other. So shear metamorphism is the rare type. The other commonly discussed type is regional metamorphism, which is what happens when you have like mountain formation, where a large area has a combination of both high temperature and high pressure. You're being squeezed together and under high temperature and pressure. And most of the areas that are affected by regional metamorphism are areas undergoing intense deformation due to various mountain building processes. So this commonly occurs at convergent plate boundaries. So here's a video about the difference between contact and regional metamorphism. How metamorphic rocks form.
All right, in this video, we're going to be talking about metamorphic rocks. Please get your rocks flowcharts ready so we can fill in our final third column. Now, recall, rocks are classified according to how they form. Igneous form from cooling and solidified magma. Sedimentary form from compacted and cemented sediments. And now our metamorphic rocks, these are ones that are going to undergo some sort of change, a metamorphosis. And what drives that change is exposure to heat, really intense heat, or pressure, intense pressure. So metamorphic rocks are rocks that are changed as a result of exposure to intense heat and or pressure. So there are two types of metamorphism that occur in nature. The first type is called contact metamorphism, and the second is called regional metamorphism. So let's talk a little bit about the difference between these two. Now, imagine you have the surface of the earth here, and you can see some trees, and these colors here, these are layers of rock underground. And so I'm going to show you how contact metamorphism works. The reason it's called contact is because it involves existing rocks coming into contact with really intense heat, which is generally provided by lava or magma. So imagine that one day an intrusion of magma forces its way up through these layers of rock. Now, all of the existing rock are going to be burned by the heat of the magma. So all along the edge of this magma, shown here in orange, you're going to have rocks that have been burned by the heat of the magma. That burning causes them to change or metamorphosize into something new. So anywhere you see the orange, you're going to have some metamorphic rock. This is caused primarily by heat. Let's fill this in on our flowchart. Okay, so the first type is contact metamorphism, and this is caused by contact with heat. Whenever a rock comes into contact with magma or lava, it is burned or metamorphosized by that heat. But let's talk about the second type, regional metamorphism. Now this one is going to be more from pressure. So let's imagine that I have a plate boundary here, a fault, a crack, and that these two plates are coming together. So it's a convergent plate boundary. Well, as you can imagine, in the middle here, there's going to be immense pressure, and that pressure can cause the rocks trapped in the middle to become metamorphosized. So all along this boundary, you'll find metamorphic rocks. Again, this is different from contact in that it's not so much about the heat, it's more about the pressure. Let's take a look at what we see here. This is a typical progression of metamorphism that occurs, starting with the sedimentary rock shale. If you add heat and pressure, it will metamorphosize to slate. If you add more heat and pressure, it will become phyllite, more, and it will become schist, even more, and it will become the metamorphic rock gneiss. Take a look at that gneiss sample down there. You'll notice it has bands of minerals. That's a result of the intense pressure. Now, if you were to take gneiss and add additional heat and pressure, it would likely melt into magma or lava, and then it would become an igneous rock. So gneiss is generally the extent of metamorphism that we see. Let's go back to our flowchart. So our second type of metamorphism is called regional metamorphism, and this is caused primarily by pressure. Of course, all of this is summarized in your reference tables on the metamorphic rock chart on page 7. You'll notice type of metamorphism, composition, what minerals are involved, how big the crystals are, whether it has banding or not, the names of the rock, and the map symbols. And of course, we'll learn lots more about this.
So the intense pressure that occurs in the metamorphism can cause the crystals to actually get squashed. So in regional metamorphism, the newly formed mineral grains end up aligning themselves in a distinctly parallel arrangement. This is called foliation. So this leads to sort of this prominent layering, or these you can get bands. And only rocks that are metamorphosed under intense pressure exhibit foliation. Specifically, you need to have differential pressure, where you have more pressure in one direction than the others. But metamorphic rocks that form almost entirely due to high temperatures will not have foliation. So things like quartzite tends not to be, quartzite isn't foliated, marble isn't foliated. Those are primarily high temperature formation processes. And the progressive patterns of foliation that develop in a metamorphosed shale serve as a good example of foliation types. You get slate under mild metamorphism, you get slaty cleavage. That's how you form slate. The shale forms a distinct, breaking into distinct flat layers, makes it great for making roofs. Then schists are a foliated metamorphic rock with larger visible grains or crystals. And then gneisses form under intense regional metamorphism, and they display banding. And the more intense the metamorphism, the larger the crystals, but the less distinct the foliation. So here's a short video about the difference between foliated and non-foliated rocks and how metamorphic rocks form.
When sedimentary rocks form, they pile up and create layers of rock. Once these layers build up, they begin to put tremendous pressure on each other. This pressure, combined with heat from Earth's interior, is going to change these rocks into metamorphic rocks. This change can happen in one of two ways. Regional metamorphism, which means it happens over a large area, so the pressure is very intense, or contact metamorphism, where the pressure is less intense since the change happens with contact with magma. Shale is a sedimentary rock that through increased regional metamorphism will change to slate, then to phyllite, then to schist, then to gneiss. Through increased heat and pressure, the minerals in the rock shale are going to change into different rocks. A few things will happen in metamorphic rocks, including that the minerals will recrystallize since they are exposed to new heat. Also, this causes foliation, which is where the minerals begin to line up and eventually form bands of the same minerals. Not all regional metamorphism is going to have foliation. For example, bituminous coal, when it changes into anthracite coal, it's not going to have foliation. The second type of metamorphism is called contact metamorphism, where various rocks will be changed by the heat from nearby magma. For example, the rock hornfels will only be made through contact metamorphism. Other metamorphic rocks that don't have foliation but can be formed by both regional and contact metamorphism are quartzite, marble, and metaconglomerate. So to summarize the rock cycle, when rock that melts into magma cools and solidifies, it becomes igneous rock. Those rocks can be broken into sediments and eventually they get deposited and buried. They then compact and cement together into sedimentary rocks. Eventually you have layers that build up, and through heat and pressure, the crystals reform into metamorphic rock. With enough heat and pressure on the metamorphic rock, it can then melt back into magma, and if it cools, well then you start the process over again with igneous rock. That's all you need to know for today. Tomorrow we are going to complete a rock cycle as part of our final work. But for today,
So here is a slate bed. You can see those clear layers. You can see how they break into nice flat sheets that will be useful for, the roof. Here's or a blackboard. Here's schist. And then here is nice. You can see the banding and the folding of the layers from the intense pressure. So that's the end of chapter 22. So minerals are composed of elements and compounds. I believe that's what the answer is. A mixture of minerals forms a rock. A particular rock that has commercial value is referred to as an ore. The two most abundant elements in the Earth's crust by mass are oxygen and silicon. Oxygen is the most common, then silicon. The most abundant mineral family is called the silicates, which are rocks that are built around silicon and oxygen. The most common example of the mineral family talked about in question 5 is feldspar. The three most common non-silicate mineral families are the carbonates, the sulfates, and the oxides. I might have not have those in the right order. And there's also the sulfides, and there's the sulfates. I get those confused. One is just sulfur, and one is a sulfide ion, which is SiO4. I mean SO4. I mean it's sulfur and oxygen. The most unreliable physical property of a mineral to use in its identification is its color. Because colors are easily changed by very small quantities of impurities. So the same mineral can have many different colors. And the arrangement of atoms and ions in a mineral is referred to as its crystal structure. A mineral's resistance to scratching is called its hardness. The ability of a mineral to split along flat planes is called cleavage. The Mohs hardness scale ranks mineral hardness with the softest mineral having a value of 1, that's talc, and the hardest mineral having a value of 10, that's diamond. And a mineral that breaks in an irregular way is said to have fracture. The color of a mineral residue left on a black or white plate is called streak and is a much better way to identify a mineral. The two main types of mineral luster are metallic and non-metallic. Metallic is shiny like a metal. Non-metallic is not. The density of a mineral compared to water is called specific gravity. The three classes of rocks are igneous, sedimentary, and metamorphic. The one that formed first on Earth is igneous, because originally Earth was molten. Molten rock found on the Earth's surface is called lava. Molten rock that's found in the Earth's interior is called magma. Igneous rocks with small crystals due to rapid cooling are called extrusive igneous rocks. Igneous rocks with large crystals due to their formation in the interior are called intrusive rocks. Exterior rocks and interior rocks. Extrusive, intrusive. The concept that geologic processes have been occurring for a long time and continue to occur today is called uniformitarianism, which is hard to pronounce. The series of changes that rocks undergo due to various physical and chemical processes is called the rock cycle. The energy for forming igneous and metamorphic rock comes from the movement of tectonic plates, which is driven by the heat of the Earth itself. And igneous rocks that are dark and contain a high percentage of magnesium and iron are called mafic rocks. While igneous rocks that are light in color and contain a high percentage of silica are called felsic rocks. The largest type of pluton that crosses many layers of rock are called batholiths. A vertical igneous intrusion into the surrounding rock is called a dike. A horizontal igneous intrusion into the surrounding rock is called a sill. A fairly large igneous intrusion that doesn't cut across layers of rock is called a laccolith. That's the one that blisters up between layers of rock. An explosive volcano is one in which its lava contains a large amount of silica and dissolved gas. And a quiet volcano is going to be one that its lava is hot, little silica, little dissolved gas. Don't know why there's a large amount there. Lava with a high viscosity contains a lot of silica and has a fairly low temperature. Quiet volcanoes usually expel basalt or mafic rock, so basalt. The type of volcano that's usually fairly short and has steep sides is a cinder cone. The type of volcano can be very large and have alternating layers of ash and lava is a composite volcano or a stratovolcano. They're just two names for the same thing. The type of volcano that has gently sloping sides but erupts frequently is a shield volcano. The process of transforming sediments into rock is called lithification, means turning into rock. The two general classes of sedimentary rock are clastic or detrital and chemical. The two types of chemical sedimentary rock are organic, coming from living things, and inorganic, not coming from living things. The class of rock that contains fossils is primarily sedimentary rock, contains fossils. The two primary agents of metamorphism are heat and pressure. The three types of metamorphism are contact, shear, and regional. If a metamorphic rock contains banding, we say it is foliated. That's the end of chapter 22. We're going to start chapter 23. As we have to get through it. Please going slowly. So, chapter 23 is about surface processes. So, surface processes are various processes that happen on the surface of the Earth. We've talked about stuff more underground. Now we're moving up to the surface. So we're going to talk about weathering, mechanical and we're going to talk about weathering. We'll just differentiate between mechanical and chemical weathering. The weathering is the breakdown of rocks. We'll talk about the chemical changes that occur in chemical weathering. We'll look at the primary agents of erosion, which are streams, glaciers, wind, and waves on the surface features of Earth. We'll trace the movement of water in its various forms through the water cycle. We'll discuss the distribution of Earth's water. We'll describe the challenges to a clean and usable water supply. We'll talk about the effects of waves on shorelines and talk about the topographic features of the seafloor. So within the context of geologic times, the Earth's surface is a very dynamic area. This is where stuff happens relatively fast. Nothing is permanent. As soon as a rock is exposed to the Earth's surface, various weathering processes begin to destroy it. Because Earth has such an active surface and active surface processes is why, unlike other planets in the solar system, we don't have lots of craters from impacts because they get worn away. Stuff gets destroyed on it. And due to various weathering processes, erosion and gravity, high places on Earth are constantly being worn down by the transportation of sediment to low places. Things are being evened out. This process is called gradation. It is making it graded, which is the term for flat. So, if someone goes and grades your lot, if you're going to build a building on something, you first grade it, you flatten the Earth in that area. Weathering is the process of the breakdown of rock exposed to the surface. So weathering, we environmental agents cause the physical disintegration, break into small pieces, or chemical decomposition, usually dissolving of a rock, of rocks and minerals at or near the Earth's surface. Weathering is generally a slow but powerful force that eventually breaks down even the most resistant materials. And rock and mineral types, moisture availability, temperature, and overall climate largely determine the rate of weathering. Weathering around here is, certain types of weathering around here is relatively quick, which is why we have so many potholes, because our climate is conductive to freeze-thaw cycles, which are good for doing physical weathering. So mechanical or physical weathering is the breaking down of rocks or minerals into smaller pieces, disintegration, without changing the chemical composition. So this is just, if you would like to mechanically weather a rock, you can take a hammer and hit it with it. You know, that is mechanical weathering. So the most common form of mechanical weathering around here is frost wedging. So frost wedging is a specific physical weathering process caused by the expansion of freezing water in fractures, joints, or cracks in rock outcrops. Basically what happens is water will flow into a crack. When water freezes, it expands by about 9% during the freezing process. This will expand the crack. Then the water can melt, travel down into the bottom of the expanded crack, refreeze, expand again. So in places like around here, where we get lots of freeze-thaw cycles, because temperature changes a lot rapidly, this can be a very effective process for the breakdown of material. And you may have seen this process occurring if you've ever frozen something in a hard container and had the container break. If you freeze like a glass bottle of water and the glass bottle shatters, that's basically frost wedging. So here is a video about freeze-thaw weathering. And this is the primary way that weathering occurs around.
Believe it or not, the rolling countryside of Cornwall in southwest England used to look more like the Himalayas or the Alps. Mountains don't last forever. They gradually wear away at a rate of about 10 centimetres every 1,000 years. So all that's left in Cornwall today is a series of domed shapes, giving the landscape its rolling appearance. Changes in temperature from day to night and the expansion of freezing water cause rocks to wear away. When water enters a crack in a rock, it expands as it freezes overnight. When the ice turns to water and freezes again, it forces the crack open a little more. As the water seeps even further, the crack widens. This freeze-thaw action is repeated. It eventually causes pieces of rock to break off. They fall down the mountainside, where they lie as pieces of jagged rock known as scree.
So here's another example of frost wedging. You get these breaking off bits, water gets in the cracks, breaks them away. Permafrost is where in certain higher latitude, cold latitude areas, you get areas that stay permanently frozen soil profiles in cold, higher latitude areas. So during the short summer season, the topsoil can thaw, resulting in wet, spongy conditions. And you get the annual freeze-thaw cycle, leads to sort of physical weathering of the top. But the permafrost itself stays solid. And you can have some very unfortunate things if that permafrost starts melting, because it can release a lot of things that are frozen away. And you can also have physical weathering being promoted by the action of things like burrowing animals and plant roots that grow and expand into rock crevices in the form of biological weathering. So here's a short video about permafrost. And you can find dramatic things in permafrost like.
Anna, we are in the northeast of Russia, deep inside the Arctic Circle, where outside at the moment it is hot enough to sunbathe. But I'm inside what is called a permafrost cave. Permafrost is the permanently frozen layer of soil that sits beneath a quarter of the northern hemisphere. And as our planet warms, and the Arctic is warming much faster than the rest of the planet, this layer of soil is beginning to thaw. And that means that the billions of tons, hundreds of billions of tons of carbon trapped inside is released. I'll show you what that means. These roots are essentially plants that were frozen in the soil at the time when the mammoths were roaming the grasslands up above. But as this stuff thaws, this decomposes and greenhouse gases are emitted into the atmosphere, methane and CO2, and that warms up the planet further. And that is why this permafrost and what happens to it is really just as important in terms of climate change in the Arctic as the melting ice caps and rising sea levels.
So that was permafrost. You can also have biological weathering, which can both be physical and chemical. So physically, tree roots and such can penetrate into cracks, but they wedge them open. Moss and things can also do that. But you can also have lichens that release acids that help break down the rock.
So looking around us here, this is an excellent example of just how weathering happens, whether through biological or other physical means. So we don't have a lot of, well, there may be a little bit of chemical weathering going on here with rainwater and stuff, but this is some fairly stable sandstone. So we got little sandstone surfaces in here still visible, but we were just marveling at how thick and dense the moss is along the side of this cliff. Okay, you can see as I push into it just how plush it is, which means that we've got generations and generations of moss that's been growing, finding every little tiny nook and cranny in that rock and forcing those cracks just a little bit wider. Eventually yellow birch seeds are able to fall onto the moss, take purchase in the moss itself, and then work its way into any cracks that happen to be wide enough in the rock. Like this tree is on there. I could probably climb that sucker, and it's only about the diameter of my leg. Then eventually, as those cracks widen open, we get rocks that are falling off here, big cracks in between the rocks here, and then entire canyons that I could literally walk into here that form between the rocks as frost wedging speeds things along and other processes encourage, as my pack gets stuck on the rock, as other processes encourage that kind of breaking open and weathering of the rock, all in place, in situ as we say, and eventually gravity will take hold and knock big chunks of those rocks off, and then other processes of erosion can get involved as well. But in the meantime, this is a great nursery of mechanical and biological weathering.
Now, chemical weathering is when the chemical composition of a rock changes, principally through reactions with water, when some of the rock dissolves, usually. So the two most important factors in chemical weathering are water and temperature. So you get the most dramatic chemical weathering in places that are hot and wet. So Southeast Asia has great really dramatic chemical weathering. Hot and wet, and there's limestone that you chemically weather. So chemical weathering is most efficient in hot, moist, tropical climates. So limestone, which is a common rock at the surface, readily undergoes chemical weathering. It occurs like everywhere there's limestone. Plenty of it happening around here as well. It's just faster and more dramatic where it's warmer and wetter. So limestone is made up largely of the mineral calcite. Normal rainwater will react with carbon dioxide in the atmosphere to form a weak solution of carbonic acid. And so H2O plus CO2 forms H2CO3. The more carbon dioxide that water comes into contact with, the more carbonic acid is formed. This is why all seltzer water or all carbonated beverages are acidic, though some are significantly more acidic because things like Coke is very acidic because there's added other acids. And then as water percolates through the soil, it can react with even more carbon dioxide that's released by various bacteria and get more acidic. And then this allows it to dissolve limestone and dissolve calcite in limestone. And as it comes into contact with calcite, CaCO3 in the limestone, then will react. So CaCO3 and calcium carbonate form calcium bicarbonate, which readily dissolves in water and gets carried away in solution. So, and most chemical weathering in limestone occurs along fractures where the most water flows. This can form underground caverns. Then the caverns can collapse, causing sinkholes, which can be quite dramatic. And this forms topography known as karst topography, which has lots of caves and sinkholes and water flowing underground. And at the most extreme, you end up with just, after lots of this chemical weathering occurs, you can end up in places where you just have pillars remaining that used to be, of what used to be a much more larger area. So there's places along the southeastern coast of Asia that have these bays with pillars in them that are formed by chemical weathering. So here are some examples of karst topography from Illinois. Watch this video and the next one, and we'll get started with the lab.
Hi, my name is Sam Pano. I'm with the Illinois State Geological Survey, and I'm a senior geochemist under the Prairie Research Institute, which is part of the University of Illinois. And in my job, I do a lot of investigations of karst areas, and I should probably tell you what karst is. About 25% of the world sits on karstified carbonate rock, like limestone and dolomite. And in Illinois, 25% of the bedrock is limestone and dolomite, with about 10% of the area having karst features. If you have carbonate rock, which is soluble in rainwater, it dissolves in rainwater, soil water, and so on. So basically, all the rocks, all the bedrock in Illinois and the entire world are fractured to some extent. And when the rainwater seeps in, or surface water, it begins to dissolve this rock. The process takes thousands of years, tens of thousands of years, millions of years. What occurs is the fractures get bigger and bigger. Then the water can seep into the bedding planes, just fairly flat-lying layers of limestone, and create caves. And the caves can be quite extensive. For example, in southwestern Illinois, there are caves that extend for 15 miles with passages that are 30 feet in diameter and rivers running through the cave. So this is the kind of areas we study.
And then an example of what can happen with a sinkhole. I will show. This is a sinkhole in Louisiana. Forming. So this is a cave that's collapsing.
Oh yeah, you said
they move it. They move it, John.
Yep, I got it.
Look,
right
I
here,
got it.
See it. It's moving that much. Oh, that's gone right there. See it right there? Look at it. Breathe, forward. Go on all in. Oh, that's a good. Look over there, John, will pass through. Well, let's get a lead. All right. Huh? You had a 1-foot wave hit it that way.
So that is where we're going to stop for today. I will end the meeting.